All right, so first thing we want to do here is we want to balance the equation. So hopefully you got 2 and 3 here. Okay. All right. Next thing you want to do is you want to determine STP. STP is when a gas is at 1 atm and 273 Kelvin. Okay. And then we have the volume of the gas, 5 million liters. And then the question is asking you how many liters of a 0.1 molarity NH3 solution do you need. So what we need to do is we need to use the ideal gas law to determine moles of our gas. And then once you have moles, you can use the balance equation to convert it to NH3. And then you can use molarity to convert it to liters. Okay, so it's a 3-step process. First step is going to be the ideal gas law. And then I'm going to rearrange it. Again, you guys don't need to rearrange it if you don't like to do that. But to this, and that'll give us moles of our gas. That's step 1. So the mole of our gas will be our pressure, 1 atm, times the volume, which is 5 million, and that's liters, divided by the ideal gas constant, so 0.0821, and then the temperature, which is 273 Kelvin. Okay. Now, real quick before we solve this out, just a reminder that you will have the equation sheet on your exam. And so you actually don't need to memorize the ideal gas law or the constant because if you take a look, you have the ideal gas law right here, PV equals nRT, and then the gas constant, 0.082, is also on there. So just a heads up about that. Okay. Did I put that in correctly? And you should get about 223,000 for your moles. Okay, so 223,000. I got 81. I'll just keep it there. And this is moles of N2. Okay, so far so good on that?
Yeah.
Okay. All right, step 2, we need to convert this into our NH3 because we have N2, but we're looking for NH3. So I'll do it a different color just so that you guys know where the steps change. But we're going to set up a fraction. We're going to use our balanced equation, 1 mole of N2 for every 2 moles of NH3. Okay, so all we got to do is multiply this by 2, and that'll give you about 446,000.
That's pretty easy.
I hope you get it right on the test.
Probably won't.
All right, and then step 3 is where we're going to use the molarity formula. Right, because we're looking for liters. We have molarity. We just found moles. And so if we rearrange this equation, liters is going to be moles divided by molarity. So 446,000 divided by 0.1 molarity. Okay, just move the decimal 1 time to the right. And then you get 446,1636. And that's going to be our final answer. All right, so here we are looking for the density of CH3, and then it gives us 800 torr, so that's going to be pressure. Okay, so 800 torr, and the temperature is 50 degrees Celsius. Okay, and what we're looking for is density, and then it tells you that they're looking for density in terms of grams per liter. Okay, so this is what we need at the very end. Our units of measurement should simplify down to grams per liter. Okay, so we're going to use the ideal gas law. So let me give you guys 1 minute. See if you guys can convert P and T into the units of measurement that we need. So take about a minute. Turn pressure into the variable we need and temperature as well. All right, guys. So for pressure, you're going to convert this into ATM. So you're going to divide by 760 because that is the conversion to ATM. That should give you about 1.05 ATM for your pressure. And then for the temperature to Kelvin, you just need to add 273. That should give you 323 Kelvin. Any questions on the conversions? Hopefully not too bad. Okay, this is where things can get a little bit trickier. Okay, because we're looking for density, right? But we don't really have a nice, easy way to go from pressure and temperature to density. So what we're actually going to be using is we're going to be using the ideal gas law. So I want you guys to just write this down on your notes because we're going to be manipulating the ideal gas law and actually combining it with a couple other equations. Okay, so ideal gas law is what we're going to work with. Okay, now before we work with the ideal gas law, we actually need to combine it with a different equation. Okay, we are looking for density, and density has grams and liters, right? If you look at the ideal gas law, we have liters, but we don't have grams anywhere, right? However, what we can do is we can actually insert grams into this equation by using a different equation that we know. We look right here, we have N, right? What does N stand for? Yeah, this is moles, right? Okay. Now, we know that there is a relationship between grams and moles, right? That's the molar mass. So we talked about this at the end of the unit, but there's a unit of measurement, or this is the variable for molar mass, mu. Molar mass is grams per mole. Okay, so jot that down somewhere because we're going to be combining these two equations in order to solve for density. Okay, molar mass is equal to grams per mole, right? It's just when we add it up on the periodic table, we just add this at the end. Now, we can actually rearrange this equation so that we can plug it into this equation right here. We know that N is moles, so what we're going to do is we're going to rearrange this so that we have moles equals grams per molar mass. All right, all we did was just kind of isolate the moles. Okay, and once we do that, what we can do is we can actually take this equation right here and plug it in to the N. Okay, so just to reiterate, we know that by itself, molar mass is grams per mole. If we rearrange this equation just to solve for moles, we can plug this into the ideal gas law to replace N with grams divided by molar mass. Does that make sense? Okay. So if we rewrote this with a combined equation, it'll be PV equals grams divided by molar mass RT. And now the ideal gas law has grams and liters, and we can solve for density. Okay, so this is going to be some algebraic rearrangement, and then we'll be able to solve from there. Okay, so what we want is we want to have grams divided by liters on one side of the equation and everything else on the other side. So let's start on the right side. We want to move RT to the other side, so all we do is divide by RT on both sides, and that'll give us grams per molar mass equals PV over RT. Okay. After that, we want to move the molar mass to the other side as well, so we can multiply by molar mass. So if we multiply by molar mass, we get that on the top of the left side, and the right side we just have grams. And then we want to move liters to the other side, so we divide by V. Okay, and if you look right here, we have G over V, G over volume, and that's how we can solve for density. So this one is tricky because first you need to combine two equations and then rearrange it so that you have a very specific set of variables on one side of the equation. Okay. All right, so just in case I lost you there for a second, let me just re-show you the math. Okay, so we got PV equals, we replace N with grams divided by molar mass and RT. You want to isolate grams and liters on one side. So we're going to divide by RT. So on the left side, we'll get PV divided by RT equals grams divided by molar mass. You want to move molar mass to the other side. So it'll be molar mass PV divided by RT equals G. And then last but not least, we move the volume to the bottom because that's liters. And so the final equation will be molar mass times pressure divided by RT equals grams over liters. And this right here is exactly what the question is asking you to solve. Okay. All right, so now that we have the final equation, I want you guys to take about 2 minutes, see if you guys can plug it in and solve for the density, okay? And see if you guys can add the correct unit of measurement because that will be part of the correct answer. So you want the number and the correct unit of measurement. Okay, so take about 2 minutes to do that, and then we'll go over it. All right, guys, so pretty much just plug and chug from here. Molar mass of CH4, you can just get that from the periodic table. C is 12, hydrogen is 1 each, so 16 grams per mole for the molar mass. Pressure is 1.05 divided by the constant, and divide it by the temperature, 323, and then that should give you about 0.63, and then the units of measuring grams per liter. Okay. Did I mess up some more?
No, I got that.
That should be close enough, but let me just double check. Did you add some more numbers than me, like 323.15? Oh, you're fine. Yeah, that's close enough. Yeah, you're good. Yeah, as long as your number is close, should be fine. All right, any questions on this? All right, one thing I do want to mention is, you see this rearrangement right here? I just took a look at the equation sheet. They updated it actually, I think last year. And so I do want to mention this is actually on the AP equation sheet. So if you guys take a look right here, they use some different variables, but right here. Okay, this is moles equals grams, and then this is molar mass, the bold italicized M, which is kind of dumb and confusing, but this right here is there. So this is the rearranged equation that we just used. It's on the AP equation sheet for you. If you want to just make a note of it, that way you don't have to do little manipulation if you don't want to. Just wanted to give you guys a heads up that it is on there. Okay. Okay, so let's move on from 10 and we'll go to 11. Ooh, my favorite topic. Okay, so this one right here, first thing we're going to do is we're going to take a look at these different gases. And what we want to do is we want to order them in terms of effusion from slowest to fastest. So we talked about this at the end of the unit. This is the kinetic molecular theory. And basically what this told us is that the lower the molar mass, okay, basically the faster they're going to move, these gases at the same temperature. Okay, and same thing vice versa. The bigger the molar mass, the slower they're going to move. Right? I gave my great fart example. Your fart is made out of different gases, and those different gases will effuse and move around at different rates at the same temperature. Okay. So based on that knowledge, see if you guys can do A, B, and C. First, you're going to put them in order from slowest to fastest. And then after that, I want you to identify which of the two gases will have the most similar rate of effusion. Okay. Take about 3-4 minutes to do that, and then we'll go over it. Alrighty, guys. Let's talk about real quick just to make sure that we're all on the same page. Yeah. Oh, did I mess? Oops. You're right. Ooh, wow, that's a big goof up. Thank you. Fastest. My bad. Okay, so just to make sure that we are all on the same page, because obviously I'm not, the lower the molar mass, the faster they're going to go because they have less mass, so they need more speed to have the same kinetic energy. Okay, so basically all we did was find the molar masses, right? And then you just put them in order from either slowest to fast, or lowest to highest, or highest to lowest, and just make sure that you denote which side is faster or slower, and don't goof up like I did. Okay, so let's go to the which two gases will have the most similar rates of effusion. You basically need to look at the molar masses, which ones have the closest molar mass. And the answer is going to be H2 and He, because the difference is just 2. It's just take a look at the difference in numbers. Even the other close ones, it's by like 4 and so on and so forth. So the two gases with the most similar rates of effusion will be H2 and He. And then your reasoning would be most similar molar mass.
Yeah, but He is twice as much as H2.
That's true, but it's still based on the mass.
But it's twice as heavy. Wouldn't it go twice as fast?
No. Because V squared. Alright, so for this one, sorry, I miswrote it. It's not Charles' law, it is Boyle's law. I apologize for the mistake. But you got two containers. They are separated. And then they give you the numbers for the gas on the left and the gas on the right, and I have them here. I even converted to ATM for you guys. Okay. Now, what we're basically doing is we're going to open the divider, and the gases are allowed to combine. And because the volume is different now, the pressure is going to change. So part A is asking, what is the final partial pressure of neon? Okay, so we are going to be, because if we take a look, we have pressure and volume, and the temperature is constant. we can just use Boyle's law. P1 V1 equals P2 V2. Now, if you don't remember it for whatever reason, if you look at your AP equation sheet, you will see at the very top of the gas section that you pretty much have it right here, right? You have P1 V1 over T1 equals the same on the other side. Now, all we did was we omitted the temperature because it is constant, so you could have just ignore that, or you can even plug it in and you'll still get the same answer. And so just letting you guys know that that's there. Okay, so we are going to rearrange the equation for P2 because that's what we're looking for. We're looking for final partial pressure. And then we're going to plug in our numbers. So for neon, our starting pressure was 1.05 ATM times 5 liters divided by the new volume, which is just the combined volume, which is 7. I think it says it right there for you. Okay, so 1.05 times 5 divided by 7 will give you 0.75. And so that is going to be your new partial pressure for neon. Okay. Everybody good with that? Okay. All right, so we're going to do the same thing for helium now because the question is asking what is the total pressure. Total pressure is going to be equal to the pressure of the two partial pressures. So there are two gases, so it'll be the pressure of neon and the pressure of helium. Okay, so we got to do the same thing again for helium, but it's pretty simple. Same equation. P2 equals the first pressure, 1.32 ATM, times the first volume, 2 liters, divided by 7 liters. So 1.32 times 2 divided by 7. That'll give you 0.38 ATM of helium. And again, if your numbers are different than mine a little bit, you're good, as long as you're close. So for the total pressure, you just need to add those two numbers together, and you should get something around 1.13 ATM. Okay. You could have also done everything in torr and then just converted at the very end, so letting you know that is an option as well. Yeah. All right, and again, I did mention this, but this will be on your exam. Good chance it'll be on the AP test as well, so it's just kind of nice to memorize how to do this. Okay. All right, let's do part C now. Okay, so if we take a look at part C, it's pretty simple. It's asking how many moles of each gas are there. Okay, assuming there's no temperature change. So super duper simple. The only equation that we have with moles is PV equals nRT. We're using the ideal gas law. And what we're going to do is we need to do this twice because it's asking for each gas. So you have to do this once for neon and once for helium. And all you're going to do is you're going to plug in the numbers that you have for each. Okay, now for this one, I would recommend just using your initial numbers instead of the final ones, just to make it a little bit simpler. But basically, since the moles of gas aren't going to change, right, because it doesn't talk about a reaction or anything, it doesn't talk about a leak, okay, the actual amount of moles of gas is going to remain the same throughout. So what you're going to do is you're going to do PV equals nRT for neon using these numbers, and then PV equals nRT for helium using these numbers. So let me give you guys about 2 minutes. Try that out, and then I'll just put the answers up there. We've done ideal gas law a lot now, so hopefully this isn't too bad. But see if you can plug in your numbers for each gas. One time for neon, one time for helium, and I'll put the answers up in about 2 minutes. Okay, try that out. So it's the same thing for neon and helium, but you just rearrange the ideal gas law, and then you plug in the values you got for neon. 1.05 ATM for pressure, 5 liters, and then constant. The temperature is 300 K for both of them, so about 0.2 moles of neon. And then for helium, same thing. The only difference really is the pressure and volume, 1.32 ATM and 2 liters. And then you get 0.11 moles of HE. Okay, so for this problem, this is that water vapor problem I was telling you about. Okay, so the first thing we want to do, I'll have you guys try part A on your own, and then we'll go over it before we go into the rest of the problem. But it's telling you basically the reaction, and you need to write the chemical reaction. It tells you that solid aluminum reacts with excess HCl to produce aluminum chloride and H2 gas. Okay, so go ahead and see if you can write the equation. You're going to have to balance it. So go ahead and try that out. I'll give you guys about 3 minutes, and then we'll go over it. If you feel comfortable moving on, please feel free to do that. But we'll do A in about 3 minutes. Alrighty, guys. So let's go over the equation for part A. So it says aluminum, so Al. It's solid, so we know that it's just a metal by itself. And then HCl, those are our two reactants, and they produce aluminum chloride. Now we know that it's AlCl3 because aluminum's most common ion is +3, chlorine is -1. So just balance that out. You get AlCl3, and then it produces H2 gas. So this right here. Okay. If you guys balance it out, you guys should get 2, 6, 2, and 3. Okay. Now I'm gonna add the states of matter. You didn't have to because it doesn't ask for it, but just so that we have it, I'm gonna add the states of matter. And that's gonna be part A. All right. Everybody good? Okay. Let's move on to part B. Now part B is the scenario that we talked about. I think this is one of our last examples of the unit, but this is going to be one of these scenarios where we're collecting gas over water. Okay, so if we can just kind of visualize what's going on, we have a container with water, right? And then what we're doing is basically we are running our chemical reaction, and it produces H2 gas, and the H2 gas basically gets trapped above the water. That's what we were talking about. Okay, it gives us these conditions for the experiment, but basically the key thing to remember is that when you collect a gas over water, you have the gas that you're collecting, so H2 in this scenario, but you're also going to have H2O gas up there as well. Okay, because water vaporizes even when it's not boiling, so there's going to be some water molecules that are trapped with the H2. If you guys remember, we talked about the wet H2 gas, right? It means that there's some water that is combined with it. And so this question is very simple. It gives you a lot of information that you'll need for the next part. But it tells you the vapor pressure of water in these conditions is 36 torr. So what this means is the partial pressure of H2O is 36 torr. Okay, and then the question is asking us for the partial pressure of H2. Okay. Okay, the last thing that we need to solve this is the atmospheric pressure. And if you guys remember, atmospheric pressure means the total pressure inside of our collection device. And so the total pressure, it tells you, is 780 torr. And if you guys remember, total pressure is equal to the partial pressures of all the gases. So 780 is going to equal the partial pressure of water and the partial pressure of H2. So this one's a very simple problem. Okay. The key thing is understanding that concept. Just remember, when you're collecting a gas over water, there's going to be some water trapped in there with it. H2O gas, excuse me. Okay, so very simple equation. You just need to rearrange it, and it'll end up becoming 780 torr minus the vapor pressure of water, which is 36 torr, and that's going to give you 744 torr for your partial pressure of H2. Okay, it doesn't ask you to give the answer in ATM, so you don't have to. You will have to convert it for the next part of the problem, but it's not a mandatory requirement to convert it in this step. Okay. Alrighty. So let me give you guys about 5 minutes to try part C. Part C is saying that if the reaction goes to completion, what is the mass of Al consumed in the reaction? So this is going to be another gas stoichiometry question. This is the first type of question we did at the beginning of class. You have a bunch of different variables for the gas. So you're going to use the ideal gas law, and then you're going to use your balance equation in order to convert and solve for grams of Al, mass of Al. So take about 5 minutes to try that out. We'll go over it, and then we'll be done with the review. Alright guys, so I got these set up for you. Pretty simple. You use PV equals nRT for all the numbers that you have for H2 gas. So pressure, you convert the 744 torr into ATM, so 0.98. The volume is 100 milliliters. You got to convert that to liters, so divide that by 1,000 to get 0.1. And then the constant is always constant. Temperature is 40 Celsius, so add 273 to get 313, and that will get you 0.0038 moles of H2. You want Al, so you use the balance equation, 3 to 2, and then the molar mass of Al is about 27, and you just dimensional analysis to the end. Okay.
Is that the last question?
Yep, and congratulations, guys. We are done with 4 and 5.